Hello everyone, this is Qianru Liao from Shenzhen University. In this video, I'm going to present our work, MagEar, Eavesdropping while audio recovery using magnetic side channel. Our work was built on the working principles of loudspeakers, so I will first give a brief overview of how loudspeakers work, and then introduce our paper. This figure shows the structure of a dynamic loudspeaker. It is composed of three critical components. The first part is the magnetic system, including a permanent magnet and T-ion. The second part is the vibration system, comprising a voice coil, a diaphragm, and a dust cap. The third part is the suspension system, including a basket as a round. When the audio current flows through the voice coil, a corresponding varying magnetic field can be generated, and combining with the static magnetic field caused by the permanent magnet, they will exert a magnetic force on the coil. Since the end of the diaphragm is attached to the voice coil, the diaphragm and the coil will move back and forth, causing the air pressure change and finally creating sound waves. During this working process, we noticed that there is an intermediate product, that is the varying magnetic field. So, we were wondering whether an detector could analyze the changes in the leak magnetic field to infer the original audio played by the loudspeaker, and we refer such a process as the magnetic side channel attack. In this paper, we proposed the prototype MagEar, an eavesdropping system that leverages magnetic side channel signals leaked by a loudspeaker to recover the intelligible human speech. And we can imagine a scenario that a victim and attacker are located not far from each other. For example, during the morning and evening rush hours, the subway or bus carriages are often crowded with passengers. The victim may be using headphones to make a phone call or listen to media, and the attacker can use a receiver coil to measure the magnetic field near the victim's headphone and apply signal processing algorithm to recover the audio contents. And besides, the attacker can also hide the receiver coil inside a headphone shell to disguise as common headphones. Since the magnetic field leaked by earphones is so weak, and varies inversely with the third power of distance, we decided to design our own receiver coil to capture such a weak magnetic field, and we considered 4 aspects of the coil for design. We first investigate the optimal geometry shape of a coil. We designed 3 types of receiver coils, each with an area of pi d squared over 4, but with different shapes. A circle, a square, and equilateral triangle. We can calculate their radius and side length respectively, and their past magnetic flux. Through the calculation, we can conclude that the circle coil has the largest magnetic flux, nearly 1.01 times that of the square and 1.02 times that of the triangle. We also manually wound 4 coils with different shapes and conducted the experiments. As shown in this figure on the left, the circular coil will generate the maximum induced voltage compared with other types of coils. Then we explored the coil center structure, spiral or cylindrical, because the complicated coil structure makes it challenging to analytically express the pulse magnetic flux. We only investigate them through the experiments. In the figures on the right, we can observe that when the diameters are the same, the spiral field coil can produce a higher induced potential, almost 2 times larger than that of a hollow coil. The third factor is the geometry size of the coil. As we all know, the induced voltage of a coil is proportional to the square of the diameter d and the number of turns n. The experimental results shown in these 2 figures also validate those relationships. However, we noticed that as the diameter increased, the voltage growth rate gradually decreased. And to explain this phenomenon, we can add a differential diameter and then increase the magnetic flux. Can be expressed as this equation. As the diameter grows, the incremental increase in the magnetic flux gradually weakens. Therefore, we can choose a coil with a high diameter performance, which means that the increasing the unit mass of the coil will result in a faster growth in the electrical potential. So considering the diameter performance and the coil size, we finally choose a coil with a diameter of 4 cm. The last part about the sensitivity and SNR of the coil. The coil sensitivity represents the change in the induced voltage due to the magnetic field strength and can be expressed as this equation. By solving this equation, we concluded that the coil sensitivity reaches its maximum when the inner diameter over outer diameter equals to 1/3. While the SNR refers to the proportion of CMR noise in the received signals. Through the calculation, we can obtain the peak value of the SNR when the inner diameter over outer diameter equals to 1/2. And therefore, we can say the ratio of the inner and outer diameter to between the 1/3 and the 1/2. After finishing the receiver coil design, we now start to introduce our system design, how we eliminate the noise and get a clean recover audio. Since each coil has its own resonant frequency, so we can adjust their resonance effect to boost the human audio bands and weaken unwanted frequency bands. The coil can be considered as a typical LC resonance circuit with a center frequency FO. And without modifying the size of the coil, we can tune the resonant frequency by connecting the coil in parallel with an external capacitor. As the external capacitance increase, the center frequency will shift to a lower value. And the figure on the left shows the frequency response curve when connected in parallel with different capacitors. And through the experiment, we have found that tuning the resonant frequency of the coil to the range of 1,500 Hz to 2,500 Hz can yield a good performance. When we recorded the magnetic signal and transferred it into the sound, we found that the converted audio was overwhelmed by the noise. In this figure above, we can observe a sharp increase to the maximum amplitude at 50 Hz and without harmonics. Considering that our power supply comes from a battery with a stable voltage, these components may be the noise from the alternating current cable, and so we use a notch filter to eliminate this power line noise. Moreover, to remove the circuit noise and the ambient electromagnetic interference, we employ the spectral subtraction for noise reduction. The spectral subtraction procedure consists of estimating the noise spectrum during the periods of silence and then subtracting this noise from the original spectrum to obtain the clean speech signal. The third stage is the frequency response equalization. Although we can achieve the noise reduction, the recovered audio is still distorted. This distortion has two causes. One is the fact that the magnetic field of the earphone is not equivalent to the vibration amplitude, and the other is the damping effect introduced by the resonance of the coil. And therefore, we use a frequency response equalizer to adjust the gain of various frequency components, which can offer a satisfying listening experience. The last step is the angle adjustment. In the previous experiments, we always assumed that the receiver coil and the victim headphones are on the same horizontal axis. However, in practice, it doesn't always work, because the victim headphones can be located in any positions, and the angular offset have a great impact on our system performance. So, to solve this problem, we propose a two-coils mode. We can have one coil on each side of the headphone shell, and these two coils are connected in series. By rotating these two coils, we can compensate from the performance loss due to the angular offset. Here's our demo, which shows the original audio and the recovered audio.
If Catherine does think of marrying again, he said, the man will have to reckon first with me. Catherine does think of marrying again, he said, the man will have to reckon first with me.
The 18-year-old inventor accepted the challenge with a smile. The 18-year-old inventor accepted the challenge with a smile.
As for the evaluation, we use English human speech audio from the library TCS as a eavesdrop content. For the speech quality matrix, we first extract the MFCC of the original audio and the recovered speech as their features, and then we calculate the cosine similarity of the two sets of coefficients to assess the similarity between these two audio samples. And therefore, the cosine similarity values are between -1 and 1. And the MobiSys is a recent advancement in automatic quality evaluation, which can predict the human mean opinion score. The calculation of MobiSys uses a score range from 1, very poor, to 5, very excellent. We also use the existing speech-to-text API to transcribe the recovered magnetic sound and obtain their transcribed text string. To evaluate the similarity between the transcribed and the ground truth text, we adopted the length-time ratio and the word error rates as the speech recognition metrics. We first evaluate MagEar for eavesdropping on 10 headphones and 5 smartphones. The distance between the coil and the eavesdrop device was varied from 20 cm to 16 cm for 8 headphones and from 13 cm to 17 cm for smartphones. The result shows that the average automatic speech recognition accuracy for headphone is 98% at 20 cm and dropped to the 74% at 16 cm. The recognition accuracy is 47% when the distance is 6 cm from the in-ear earphones. For the smartphones, the average ASR accuracy is 95%, and the average word error rate is 30% at 13 cm. When the distance increased to 17 cm, the average accuracy decreased to 18%, and the average word error rate increased to 37%. And then we demonstrate the MagEar's eavesdropping ability when there is an obstacle between the MagEar and the victim device. The results for the headphone and the smartphone are presented in these two figures on the left. It can be seen that the obstacle has a negligible effect on the magnetic side channel eavesdropping. The reason is that the conductivity of these obstacles is low, so the magnetic signals can pass through them without any significant loss. And next, we evaluate the MagEar in different environments, including a park, a coffee shop, a restaurant, and a private home. As shown in this table, the recovered audio quality suffers a certain degree of degradation in the indoor scenarios. Thanks for your attention. For more details, please refer to our paper.